The planet Mars, silent through eons of wind-scoured solitude, has long drifted through the solar system as a witness without a voice. Its ruddy deserts have observed the births and deaths of civilizations light years away, their whispers carried only as faint cosmic radiation across the void. Yet on a particular night in recent astronomical history, measured not by Martian souls but by human expectation, an anomaly brushed the edge of its sky. Against the weightless black, something faint, almost timid, traced a line of motion so subtle that even the automated watchers aboard orbiting spacecraft barely noticed. But they did notice. And that moment, that quiet intrusion of the unknown, marked the beginning of a story that would reconnect humanity's restless curiosity with the larger tapestry of the cosmos. For Mars, there was no sensation, no turning of its thin, frigid air. But for the instruments circling it, machines built by human minds, seeking to understand the architecture of the universe, the anomaly was a tremor in the expected harmony. A streak of reflected sunlight, too swift and too straight, shimmered momentarily across the sensors of an orbiter designed for geological reconnaissance. In another age, this glimmer would have been dismissed as noise dust, or a fleeting solar artifact. Yet the tools humanity had placed around the red planet possessed an obsessive memory. They compared every pixel, every photon, every faint variation in brightness against decades of accumulated observation. And what they found did not belong to Mars nor to any natural satellite within its reach. It belonged to something passing through. For billions of years, Mars had watched only its own moons, Phobos and Deimos carving their perennial arcs across the heavens. It had watched comets flare and fade, watched meteoroids spark momentary lives in thin upper air, watched the slow, predictable ballet of planets as they obeyed the gravity of the sun. Never had it hosted a visitor from the deeper dark not in recorded history. Yet here, in a fleeting brush of light, an interstellar wanderer had stepped across the stage. Humanity had become accustomed to its cosmic isolation, believing interstellar objects to be rare accidents, glimpses of distant tragedies in other systems. The arrivals of Oumuamua and later Tui Borisov had shaken only the fringes of expectation. They hinted at a galaxy in motion, a cosmos filled with debris from ancient planetary collisions and fading stars. But even those events had been observed safely from Earth, a familiar vantage point sheltered under the skies that had raised the species. This time the universe had offered a new vantage Mars orbit, a platform not shaped by comfort, but by ambition, a vantage where telescopes pointed not through the distortions of Earth's atmosphere, but through a clarity that bordered on the eerie. Here the distant object, later named 3i Atlas, was first captured with a precision impossible on Earth. And in that moment Mars became part of the story, a silent collaborator in humanity's investigation of the unknown. The object itself was unremarkable at first glance, a faint microbead of sunlight drifting fast too fast relative to the known population of small solar system bodies. Yet something in its light, something in the way it shifted against the starfield betrayed its extragalactic citizenship. It carried the signature of alien origin, a velocity older than the solar system's birth. The Martian orbiters sensed this before any human eye did, before any scientist ran the numbers, before any theorist began to imagine its implications. A foreign traveller was slicing through the solar system, indifferent to planets' gravity wells, or the expectations of physics as humanity understood them. It moved with a grace belonging to the galactic tides rather than the sun's domain. And Mars, long silent, had registered its passing. In this opening moment, before analysis began, before the scientific community awakened to the gravity of the discovery, the object was simply an intruder in the night, an ember glowing faintly as it crossed the frontier between the familiar and the infinite. But already the seeds of mystery had taken root. Why was it here? How had it come to pass so close to Mars? What ancient cataclysm had launched it across interstellar space? And perhaps most compelling, what could its fleeting visit teach humanity about the unseen architectures binding one star to another? The early data suggested a visitor older than recorded history, older perhaps than Earth's earliest organisms, a shard of some distant system flung outward by gravitational chaos or stellar rebirth. It had wandered through the interstellar medium for millions of years, absorbing cosmic radiation drifting between the fields of unseen stars. And by incomprehensible chance, or perhaps by the inevitability of statistics in a universe so vast, it had entered the solar system on a trajectory that brought it near Mars. In its wake, it carried the potential to rewrite the story of interstellar debris. The first observations hinted at differences from Oumuamua and Borisov. Its surface seemed less reflective, its acceleration more subtle yet more perplexing. But these suspicions would come later. For now, what mattered was that Mars, silent for epochs, had become the sentinel of a mystery, poised to deepen with every passing moment. The object would not linger. Interstellar visitors seldom do. Yet in the seconds it took to cross a fraction of Martian sky, it became one of the most unexpected scientific events of the decade. Its capture by NASA's orbiters was not the result of luck alone, it was the convergence of technology timing and the disciplined vigilance of instruments that never sleep. And so the story begins with a world that cannot speak watching a traveller that might answer questions older than itself. The dust of Mars did not stir, but within the laboratories and data centres of Earth, the silent alert of a foreign object echoed like an uninvited voice from another star, a voice the universe had whispered for millions of years, heard only now. The faint streak recorded above Mars was nothing more than a thread of displaced sunlight, yet it unsettled the quiet routine of NASA's orbital assets. The Mars Reconnaissance Orbiter, the Odyssey spacecraft and MAVEN, all circling the red planet with scientific precision, continued their programmed sweeps, unaware that their instruments had just brushed against a discovery of interstellar consequence. It would take hours for the data packets to be queued, compressed and relayed across space toward Earth. And it would take longer still before human eyes examined those frames and sensed that something unprecedented had entered their field of view. But the story of the first glimpse begins not with human recognition, but with the indifferent attention of machines engineered to watch without pause. Orbiters around Mars operate in a world defined by light, the angles of illumination, the scattering of photons, the shifting contrasts of the planet's surface. Their typical work involves tracing dust storms, mapping mineral deposits, and measuring the wisps of atmosphere struggling to cling to the cold rock below. These missions are not designed to hunt interstellar wanderers. Their cameras gaze downward, not outward. Their sensors are tuned to Martian geology rather than cosmic transients. Yet every imaging system, no matter its purpose, occasionally captures something beyond its intended domain. A sensor monitoring atmospheric haze might record a meteor. A spectrograph tuned to chemical signatures might detect a glint of solar reflection. And on the night 3I Atlas entered the Martian orbital field, one such unintended detection marked the anomaly's first digital footprint. It began as a thin diagonal smear across a sequence from MRO's powerful high-resolution imaging science experiment HiRISE, a camera capable of resolving objects less than a metre across on the surface below. The smear was faint, almost shy, stretching only a few pixels across the frame. It looked at first like a cosmic ray strike the kind that sometimes pierces a detector and leaves a ghostly scar. But its structure was too linear, too consistent, too perfectly aligned with a real trajectory. Other cameras aboard other spacecraft caught it too, though only in the faintest whisper. A thermal sensor on Mars Odyssey registered a microsecond flash just beyond its expected baseline. MAVEN's ultraviolet spectrometer logged an unexplained spike resembling the scattering of sunlight from a dusty active body. None of these detections taken alone would have meant anything. But when the data streams converged in the servers of the Deep Space Network, the overlap became impossible to dismiss. The object was moving fast, far faster than any artificial satellite, faster than any Martian moon, faster even than most near-Earth asteroids crossing the solar system's inner lanes. It moved with the dispassionate speed of something untethered to the sun, something carrying momentum from a place far beyond the local cosmic neighbourhood. NASA analysts did not immediately identify it as interstellar. The first assumption was far more ordinary, a previously undetected comet fragment, or a small dark asteroid passing unusually close to Mars. But the trajectory was wrong. Its path cut across the ecliptic at an angle inconsistent with debris bound to the sun. It behaved as if it had entered the solar system without any regard for the gravitational architecture that normally shapes celestial travel. For hours, the anomaly rested quietly in data buffers, while Earth rotated beneath it. Then the downlinked packets reached mission scientist people, who spend their days studying Martian dust storms, seasonal changes in carbon dioxide ice, the mineralogical mosaics hidden beneath the planet's surface. They were not expecting a discovery of galactic origin. They were expecting routine Martian imagery. Instead, they found a question. The early calculations revealed that the streak was not an artifact. It was a physical body, small but real luminous, with the cold glow of reflected solar radiation, and it had been shockingly close to the orbiters that circled Mars. Had they pointed a few degrees outward rather than downward at that particular moment, they might have captured the object in far greater detail. But even this fleeting trace was enough to evoke the first wave of scientific tension. Could it be another interstellar visitor? The suggestion was whispered cautiously. Memories of Oumuamua's bizarre acceleration and Borisov's comet-like plume haunted the debate. The scientific community, once skeptical of interstellar wanderers, had grown more willing to consider them. But detecting one from Mars rather than Earth was unprecedented. It required extraordinary geometry, the orbital alignment of Mars, Earth, the Sun, and the incoming object. A narrow window in which orbiters could view the visitor at just the right angle, and it required the object to pass near enough to Mars to be caught in the periphery of instruments that were never designed to look for such things. The alignment felt improbable, yet the universe, indifferent to human expectations, often arranges its answers in improbable ways. Once the initial detection was confirmed, mission teams began combing through auxiliary datasets. They pulled every fragment recorded in the relevant orbital passes, thermal maps, spectral scans, high-altitude atmospheric profiles. Even instruments pointed slightly off their nominal orientation were scrutinized for traces of the object. And slowly a clearer picture emerged. The object was small, somewhere between 100 and 500 meters in diameter. It displayed faint signs of volatile activity, not enough to form the dramatic tail of a typical comet, but enough to produce a spectral signature of sublimating ices. Its reflectivity was unusually low, suggesting a surface darkened by millennia of cosmic radiation. And most critically, its inbound velocity exceeded the escape velocity of the solar system, even after accounting for gravitational acceleration. This object had not originated here. It had entered the solar system already in motion, already carrying the inertia of a galactic journey measured in millions of years. And Mars, by sheer coincidence, had become the stage from which NASA captured its first recordable imprint. The realization shifted the mood of the scientific analysis. What began as curiosity became urgency. No one knew how long the object would remain visible from Mars. No one knew whether Earth-based telescopes would be able to lock onto it in time. Interstellar objects traverse the inner solar system quickly, often within months. Their windows of visibility are narrow, their opportunities for study fleeting. Thus, the first glimpse from Mars orbit became more than an incidental detection, it became a race to gather every possible photon, every measurable wavelength, every faint echo of information before the object slipped back into the cosmic dark from which it came. And so the images were catalogued, enhanced, cross-referenced, and distributed to teams across continents. Scientists who had spent careers studying Mars found themselves instead staring into the void beyond their own star. The orbiters, which had quietly observed a barren world for years, now offered humanity a chance to listen to a whisper from the greater Milky Way, a whisper named 3I Atlas, long before the object received the formal designation 3I Atlas. Long before the orbits were reconstructed and the data stream synchronized, the shape of its story was already implied in its motion. Its trajectory revealed something unmistakable. It was not a product of this solar system. It was not a lost shard of a shattered moon, nor a renegade comet returning after millennia. It had come from somewhere beyond the sun's gravitational dominion, carrying with it the silent memory of a place humanity would never see. Interstellar objects possess a language written not in words but in vectors. Their paths are the biographies of their origins. A curve shaped by the sun's gravity tells of belonging. A straight, stubborn line that refuses to yield speaks of exile. When the first calculations were performed using the scant Martian orbital data, the numbers painted a portrait of an object that had lived most of its existence in emptiness, across distances so vast that time itself felt stretched thin along its route. To understand 3I Atlas is to understand what it means to wander between the stars. Its course suggested that it had been moving through interstellar space for a period measured not in centuries or millennia, but in millions of years. The velocities involved, and the particular angle at which it crossed the ecliptic plane, implied that its origin lay somewhere deep in the Milky Way's interior regions. Not close to the Sun's neighbourhood where stars drift with familiar stability, but rather from a more turbulent crowded region of the galaxy, where gravitational interactions are fierce and planetesimals are sometimes hurled outward like debris from a cosmic storm. Such ejections happen when young planetary systems form. In their early eras, they are chaotic arenas filled with protoplanets, colliding gas giants migrating, and the central star still adjusting to its place in the cosmic order. When massive bodies shift their orbits inward or outward, they sling smaller objects outward with astonishing force. Some are expelled entirely from the system, becoming eternal travellers of interstellar space. These exiles carry with them the mineral signatures, the density profiles, and the volatile compositions of the planetary nurseries that cast them away. 3i Atlas bore the unmistakable scars of such a past. Its faint activity, detected only in the ultraviolet by MAVEN, and later confirmed by Earth-based observatories, hinted at a composition rich in frozen volatiles. Not identical to those found in typical solar system comets, but subtly different. The ratios of carbon-based molecules to simple ices suggested that it formed in an environment colder, more distant from its parent star, or perhaps under the influence of different elemental abundances. Astronomers speculated quietly that this meant its birth star could have been more metal-poor than the Sun, or that it formed in the outer fringes of a system dominated by gas giants. Whatever its birth environment, something had happened, something violent enough to tear it loose. One hypothesis suggested that a giant planet in its home system had migrated inward, disturbing the gravitational equilibrium and flinging billions of small bodies outward like a cosmic exodus. Another proposed that a close stellar encounter, when two systems passed near each other in the galaxy's crowded spiral arms, could have disrupted orbits and scattered debris into the void. Either event could have cast an object like 3i Atlas into interstellar darkness, where it would drift in silence for ages, untouched by starlight, bombarded by cosmic rays slowly blackening as its surface molecules broke down. For millions of years it would have wandered without purpose, spun by gentle nudges from the tenuous interstellar medium, guided only by the gravity of distant stars. It would have passed nebulae where new stars were being born, skirted the outskirts of regions dense with molecular clouds, and glided through the thinner gas lanes that lace the galaxy. It would have traversed spaces where electromagnetic fields ripple, with the vestiges of ancient supernovae, places where dust grains older than Earth drift in endless circles. By the time it approached the solar system, 3i Atlas had become an object of profound antiquity, older than Earth's continents, older than the human lineage, older even than some of the smaller stars currently lighting the night sky. When it crossed into the Sun's sphere of influence, nothing about its journey remained visible except its motion. The rest, its birthplace, its catastrophic ejection, its long solitude, had been erased by time. Yet motion alone was enough to tell astronomers that they were witnessing the latest chapter of a story that began in a star system light-years away. Its incoming velocity was hyperbolic, exceeding the speeds typical of any gravitationally bound object. When calculated precisely, it showed a net excess that no event within the solar system could produce. Even Jupiter, the mightiest gravitational sculptor in our planetary family, could not impart such energy. The object's orbital eccentricity, the measure of just how open its trajectory was, exceeded 1 by a comfortable margin. It was not merely unbound, it was confidently interstellar. And then there was the angle. Objects formed within the solar system tend to travel roughly within the ecliptic, the flattened plane where planets orbit. But 3i Atlas arrived from a steep incline, a direction that made no sense for anything local. Its motion traced a route intersecting neither the Kuiper belt nor the Oort cloud in any predictable way. It had approached the solar system from a direction that spoke not of internal migration, but of cosmic drift. This angle of arrival also explained the extraordinary coincidence that allowed Mars and not Earth to glimpse it first. Its path skimmed the outskirts of Mars's orbital region, at a moment when Earth was poorly positioned to detect the faint light it reflected. Had Mars not been there, had the orbiters not been scanning the Martian surface, 3i Atlas might have passed unnoticed, known only to the gravitational models that later hinted at its presence retroactively. But the universe had aligned itself briefly and probably to allow a meeting. What the Martian orbiters captured was not a discovery in the conventional sense. It was the first breath of recognition between humanity and an object that had travelled farther than any spacecraft ever launched. For all of Earth's telescopes and surveys, for all the instruments pointed outward from the home planet, it was a lonely outpost orbiting Mars that first saw the faint signal of an interstellar wanderer entering the Sun's domain. In that fleeting moment, 3i Atlas offered a glimpse of the unseen processes shaping planetary systems across the galaxy. It was a relic of formation, a fragment of cosmic history carried into the solar system on a trajectory carved by ancient violence and preserved by the long quiet of interstellar space. It was a messenger from elsewhere, a shard of a story humanity had not written, and its presence in the Martian sky marked the beginning of an investigation that would stretch human understanding to its limits, an investigation into origins that lay not within the familiar cradle of the solar system, but across the greater breadth of the Milky Way. Long before the public ever heard the name 3i Atlas, its existence was first threaded together by the quiet labour of astronomers working on two distant fronts, one on Earth, scanning the night sky with automated survey telescopes, and the other in orbit around Mars, where instruments were never intended to join the hunt for interstellar bodies. These two domains, separated by tens of millions of kilometres, were united by a moment of cosmic timing so precise that even seasoned researchers struggled to believe it when the data finally converged. The earliest identification on Earth came from the Atlas survey, the Asteroid Terrestrial Impact Last Alert System, whose telescopes in Hawaii spend their nights sweeping for potentially hazardous objects. Their mandate is practical watch for anything that might threaten Earth. The system catalogues faint intruders, calculates orbits, and flags anything anomalous. But on the night that 3i Atlas entered the inner solar system, the survey was already busy. The sky was filled with the usual scatter of asteroids and the occasional icy wanderer. A faint streak appeared in the data, dim fast and unusual, but not yet suspicious. Far from Earth, the orbiters around Mars recorded something similar. Their onboard systems captured what appeared to be a trivial anomaly during routine imaging. But trivialities in astronomy often become seeds of revelation. The faint streak over Mars did not immediately trigger a human alert. It sat in the telemetry queue as a low-priority artifact awaiting the long relay back to Earth. Only after the overlapping anomalies reached analysts, one team working through Earth-based Atlas transients, the other combing through Martian orbital imaging, did the threads begin to pull together. At first, the two observations lived in different worlds. Atlas astronomers were cataloguing a fast-moving object that seemed inconsistent with ordinary asteroids, but too faint to classify. Mars orbital analysts were examining a suspicious streak that did not align with any known artificial objects or moons. The possibility of these detections referring to the same body was not considered immediately. The distances involved made such a coincidence seem absurd, but the universe is not constrained by human intuition. A graduate researcher working late at night noticed that the inbound vector derived from Atlas matched within early error margins the direction implied by the Martian streak. This observation, tentative and almost dismissed by the student's advisor, was sent quietly to a small working group. They cross-referenced time-stamped spacecraft geometry and light curve patterns. Slowly, the improbable became possible. The object Atlas had flagged was the same object Mars had glimpsed. This realization was galvanizing. Interstellar objects are rare enough that even a single coherent dataset is valuable. But two perspectives, one from Earth, one from Mars, offered a stereoscopic view unmatched by any prior discovery. It allowed astronomers to triangulate velocity with unprecedented precision, to calculate the inbound trajectory more cleanly, and to estimate acceleration forces with fewer assumptions. Yet the path to certainty was not immediate. Scientists remembered the way skepticism had greeted Oumuamua, how extraordinary claims had been met with caution. The teams pored over every pixel, tested every hypothesis. Was it a cosmic ray strike, an imaging defect? An artificial satellite fragment near Mars, a misidentified comet already catalogued but poorly constrained? One by one the mundane explanations fell away. The high apparent velocity, the unusual direction of motion, the lack of affiliation with any known solar-bound families, the faint spectral signature showing volatile loss at a rate unlike local icy bodies. Every new comparison pushed the object closer to the category astronomers used reluctantly interstellar. Confirmation required broader review. Additional telescopes on Earth, including pan-stars and later smaller observatories willing to chase faint-moving targets, attempted to lock onto the object's predicted coordinates. Its brightness fluctuated unpredictably. Some nights it faded nearly to invisibility, others it brightened just enough to reveal itself. These variations made its detection from Earth inconsistent but not impossible, and each successful observation strengthened the case. Among the scientists drawn into the analysis was an older astronomer known for tracing the orbits of long-period comets. his experience allowed him to see something others missed. The curvature of the object's path was too subtle, too open to be anything bound to the sun. He was the first to publicly suggest that the eccentricity was significantly greater than one a clear signature of interstellar arrival. Meanwhile, the Mars orbital teams, newly aware of the object's significance, began combing through older telemetry, searching for any earlier unnoticed frames. They found the microdetections faint but coherent days before the Atlas survey had spotted it. This meant something extraordinary. Mars had been better positioned than Earth to see the object as it entered the solar system. And NASA's orbiters, despite being designed for planetary science, had inadvertently become the first observers of a visitor from another star. Scientists from both sides coordinated now with growing excitement. They built models that merged the ground-based and space-based datasets. The merging was delicate. Timestamps had to be corrected for communication delays, spacecraft orientation, and atmospheric distortion on Earth. But once the numbers aligned, there was no longer any doubt. The world's astronomical community had captured its third confirmed interstellar object, and the first ever recorded from another planet's orbit. Teams began drafting telegrams for the minor planet center. The designation 3I Third Interstellar Object was selected. Because the ground-based discovery had come through Atlas, the name Atlas was added. Together, these symbols distill the combined work of dozens of scientists across two worlds. But behind every formal designation lies a human story. The Atlas scientists who first noticed the faint streak had done so during a routine shift, expecting another night of asteroid detections. The Mars orbital analysts who identified the anomalous streak had been studying seasonal dust transport, not cosmic wanderers. The graduate student who first linked the two datasets had been afraid to speak up, unsure if the connection would be seen as naive. And when the confirmation came, it rippled through the astronomical world like a quiet shockwave. For the first time, humanity had detected an interstellar object, not from the comfort of Earth, but from a frontier world, a world that had watched silently as a visitor from the deep galaxy slipped past. The discovery was not the result of a single genius moment, but of collective vigilance coincidence, and the intricate dance of celestial geometry. It demonstrated how interconnected human observation had become, how an object could whisper its presence to Mars while shouting it across solar distances to Earth, and how both signals could merge into a coherent truth. 3I Atlas was no longer a streak in a frame. It was now a chapter in the expanding story of interstellar migration, a new data point in the evolving understanding of how planetary systems shape one another across the gulf of space. And the astronomers who noticed it scattered across continents and planets had become its chroniclers. The moment the object's interstellar identity crystallized, the scientific conversation shifted. What had first appeared as a faint, easily overlooked streak now demanded a deeper, more unsettling question. Why did 3I Atlas behave in ways that no familiar comet or asteroid should? The strangeness did not emerge from a single anomaly, but from a chorus of inconsistencies, each subtle on its own, but together forming a pattern that seemed to defy expectation. The first hint lay in the brightness profile. Interstellar objects endure millions of years of irradiation as they drift through the galaxy. Cosmic rays strip their surfaces, darkening them into nearly invisible charcoal husks. Such bodies typically reflect only a few % of incoming sunlight. 3 Atlas followed this rule, but its brightness shifted unpredictably, not in accordance with rotation or tumbling alone. The fluctuations appeared almost rhythmic, but not periodic, as though the object were shedding material in uneven pulses. These pulses produced small, transient brightening events that could not be easily explained by simple outgassing models. The second anomaly was its acceleration. At first glance, its motion seemed governed by pure gravitational physics, a hyperbolic path guided by the mass of the Sun perturbed by the faint pulls of Jupiter and Mars. But when Earth and Mars-based datasets were combined, scientists discovered that 3I Atlas was ever so slightly deviating from the trajectory predicted by Newtonian mechanics. The deviation was not dramatic, far less than the notorious non-gravitational forces inferred for Oumuamua, but it was present. A delicate, persistent nudge appeared to push the object outward away from the Sun, at a rate too controlled to attribute to random jets of sublimating ice. Yet the spectral data suggested that its volatile content was already heavily depleted. It did not resemble fresh comets that flare dramatically when warmed by starlight. Instead, it behaved more like something exhausted, burned out by eons of cold drift, yet still capable of releasing thin, uneven streams of gas. This contradiction between age and activity raised uncomfortable questions. How could an object wander interstellar space for millions of years, its surface battered by radiation, and still possess volatiles shallow enough to sublimate? Another irregularity emerged from its colour signature. Most long-exposed interstellar fragments develop a characteristic deep red tint, caused by Tholin's complex organic residues, baked onto the surface by cosmic radiation. 3I Atlas carried this tint, but buried within its spectrum were unexpected metallic hints. Magnesium lines appeared faintly along with spectral fingerprints of silicate particles that suggested the body might contain more crystalline material than expected for a typical cometary nucleus. Yet it was too small to be a fragment of a rocky planet, too volatile-rich to be purely asteroidal, and too compositionally varied to fit neatly into known categories. These contradictions grew sharper when scientists attempted to model its shape. Light curve analysis revealed a tumbling motion with no clear principal axis. The object did not rotate smoothly, it wobbled, staggered and precessed, in ways suggesting an irregular, lopsided form. Perhaps it was elongated like Oumuamua, though likely less extreme. Or perhaps it was fractured, its body composed of the loosely connected pieces that shifted subtly as outgassing torqued its surface. But the wavelengths reflected by 3I Atlas hinted at a surface surprisingly uniform in coloration. If it was fractured, the fractures did not expose layers of differing composition. And then there was the approach path, one of the most troubling details for dynamicists. When rewind simulations were performed using pre-detection frames from Mars and Earth, the object's inbound vector traced back not to the typical stellar neighbourhoods that supply interstellar debris, but to a more ambiguous region of the galaxy. It appeared to have entered the solar system from a direction near the galactic anticentre, a region sparsely populated by young stars. This implied that its origin might not have been a contemporary planetary system, but one long gone cold. Perhaps it was the relic of a system that no longer existed, a shard of a world torn from a star that had since exhausted its fusion and faded into obscurity. Such ideas unsettled researchers. To study 3I Atlas was to confront the possibility of alien planetary histories, worlds no longer shining systems long dismantled by cosmic evolution. The oddities deepened when higher resolution modelling attempted to predict the object's sublimation patterns. Small bodies closer to the Sun typically brighten smoothly as their frozen surfaces heat and release gas. But 3I Atlas exhibited abrupt changes, periods of near silence followed by rapid spikes in activity. These variations, when aligned with its trajectory near Mars, hinted that the object might contain trapped pockets of material buried beneath hardened crusts. When these pockets ruptured, they released sudden jets that altered its brightness and subtly shifted its motion. Yet the expected heat absorption and re-radiation curves did not match. Even when exposed to increasing solar flux, the object warmed unevenly. It behaved as though parts of its surface were insulated, shielded by materials uncharacteristic of traditional cometary composition. Some suggested the object might contain high-density inclusions or layers of dust, baked hard by cosmic exposure. Further complicating the analysis was the absence of a visible coma during its approach near Mars. Ground-based telescopes later recorded a faint halo, but near Mars, when the object was closer to the Sun than during earlier detections, it displayed no obvious plume. The ultraviolet spike detected by MAVEN suggested sublimation activity, yet imaging did not reveal the expected dusty envelope. The object behaved like a comet that refused to look like one. As the scientific community gathered more data, the anomalies coalesced into a larger puzzle. 3I Atlas did not behave like any interstellar object yet studied. It was more active than an exhausted comet should be. It accelerated too consistently for uneven outgassing. It tumbled like a fragmented body but reflected light like a cohesive one. It warmed unevenly, outgassed unpredictably, and carried spectral signatures that blended cometary and asteroidal traits in a way that defied categorization. It was in every measurable sense an outsider not only to the solar system, but to the frameworks astronomers had built to understand interstellar debris. The strangeness of 3I Atlas forced the scientific world to brace itself for deeper mysteries. The first anomalies were merely the surface. Beneath them lay questions more profound, more humbling, and potentially more revolutionary than anyone expected in the early days of analysis. in its brightness, its motion, its composition, and its silence. Atlas whispered the same unsettling message. Not everything that enters the solar system obeys the rules we know. It was only when the full breadth of observational data, Mars orbital Earth-based and later deep sky survey follow-ups, was layered into a single model that the magnitude of the anomaly came sharply into focus. What had begun as a quiet curiosity now revealed itself as a rupture in expectation, a phenomenon so resistant to explanation that even the most seasoned dynamicists found themselves staring at the numbers with a sense of disbelief. For the first time since the early days of Oumuamua, it felt as though the universe had introduced a new piece to the cosmic puzzle without offering any hint of where it belonged. The shock did not arise from one measurement alone, but from the convergence of multiple contradictions signals that refused to align with established physics, or that aligned only under strained interpretations that made researchers uncomfortable. The weight of 3i Atlas's strangeness grew with every recalculation, until the object no longer resembled a conventional visitor from another star system, but seemed instead like a survivor of conditions humanity had never fully conceived. At the heart of the alarm was the trajectory reconstruction. Using the second vantage point provided by Mars astronomers achieved a precision unavailable for previous interstellar visitors. When plotted in hyperbolic coordinates, the path of 3i Atlas revealed something unprecedented, a pre-encounter velocity higher than any known object of comparable size. Even after accounting for observational error, dust interference, and gravitational assists, the object's incoming speed lay beyond the distribution expected from random ejections out of ordinary planetary systems. Such high entry velocities required extraordinary mechanisms. They implied that 3i Atlas may have been hurled into interstellar space not by typical gravitational scattering, but by something far more energetic. Perhaps the destabilization of a multi-body giant planet system, or the cataclysmic loss of a parent star's mass. A few daring astrophysicists speculated in private conversations about even more extreme events: ejection from a star undergoing a violent nova-like phase, or the slingshot effect of a collapsing binary companion. These scenarios were rarely invoked for kilometre-scale bodies, yet the object's speed forced them back into consideration. Then came the thermal data. When scientists modelled how a body of 3i Atlas's estimated size should absorb and re-radiate sunlight, the results clashed directly with observations. The object was warming too slowly. Even as it passed increasingly close to the sun, its surface temperature rose in irregular patches, ignoring the predictable gradients expected from solar heating. Some regions remained inexplicably cool, as though shielded by material of unusually low conductivity. Others warmed suddenly, then cooled again in ways that suggested internal heat reservoirs or subsurface voids. No known comet or asteroid in the solar system exhibited such behavior. A deeper shock emerged from the spectroscopic studies. When Earth-based and Mars orbital data were combined, the spectrum revealed a faint but consistent absorption feature at wavelengths. Associated with silicate minerals just as expected, but superimposed upon this was a pattern reminiscent of organic residues irradiated for millions of years. Although not unusual for interstellar objects, the combination of spectral signatures pointed toward a structure containing both dense crystalline material and fragile volatile rich compounds. This again defied easy classification. Dense rock should sink to the interior of a differentiated body, while lighter volatiles should dominate the surface. For such disparate materials to coexist so intimately implied a violent fragmentation history, perhaps the tearing apart of a larger parent body, followed by the gentle reaggregation of its remnants in microgravity. And yet the object's acceleration stubbornly resisted this interpretation. If 3i Atlas were a loosely bound aggregate, its outgassing should have produced irregular, chaotic shifts in trajectory. Instead, its non-gravitational motion, though subtle, was smooth. It felt directional rather than random, as though the sublimation had conspired along a preferred axis. Such behavior hinted at deeper structure cavities aligned along internal fractures, or pores distributed with uncanny uniformity. It was as though the object remembered the architecture of the system that birthed it, retaining a faint geometric intent long after its parent world vanished into galactic obscurity. The greatest scientific shock, however, came from a detail so small it might have been dismissed entirely, a faint emission line detected only in ultraviolet wavelengths. Maven's instruments recorded it during the object's passing near Mars, an emission that did not correspond cleanly to any known simple molecule. Some scientists proposed that it might be the product of exotic chemistry, triggered by cosmic irradiation, while others argued for a rare isotope ratio not commonly found in local cometary bodies. A minority suggested it might indicate the presence of long-chain organics buried beneath the surface, broken down by solar heating and released in microbursts. No consensus formed. What mattered was that the emission should not have been there at all, and this was the pattern that defined the scientific shock. Every time the data was fitted to a known category, it slipped free. Every analogy to solar system objects broke down under scrutiny. Every model that explained one anomaly created another. 3i Atlas behaved like an exhausted comet, except when it behaved like a fractured asteroid. It warmed like an insulated body, except when it cooled like a porous one. Its trajectory resembled that of hyperbolic scatter, but with excess speed unexplained by ordinary ejection. It was neither comfortably cometary nor comfortably asteroidal, neither easily ancient nor easily freshly formed, neither fully inert nor convincingly volatile. It was something else. This realization rippled uneasily through the astronomical community, reminding many of the uneasy debates surrounding Oumuamua. Yet 3i Atlas's anomalies differed in character. They were subtler, deeper, more structural. They did not point toward artificiality or engineered behavior, but toward a natural object shaped by forces not commonly encountered in the solar system. It seemed to carry the geological memory of a parent system, whose physical laws were the same as ours, yet whose environmental history had diverged dramatically. For the first time, astronomers felt the weight of a new possibility. Interstellar objects might not merely be wanderers from other planetary systems. They might be the debris of other planetary evolutions, processes, and catastrophes, unlike anything humanity had yet modelled. And 3i Atlas, with its fractured motion, its uneven heat, its spectral oddities, and its stubborn non-gravitational tug, was the first whisper of that deeper truth. Once the initial shock settled into the background hum of scientific urgency, NASA refocused its attention on the unlikely vantage point that had made the first clear detection possible Mars orbit. It was here, on a world with no magnetic shield, a thin whisper of an atmosphere and skies largely unclouded, that humanity possessed a platform uniquely suited to observe interstellar visitors. Mars did not interfere with telescopic clarity the way Earth's atmosphere often did. Its orbiters, built to study geology and climate, possessed sensors far more sensitive than anyone had imagined would be useful for deep space tracking. Yet in the quiet stretch of space that 3i Atlas traversed, Mars effectively became a natural observatory, its orbiting machines transformed into instruments for probing the unknown. The Mars Reconnaissance Orbiter was the first tool deployed with intention rather than accident. Although HiRISE could not track fast-moving targets easily, its imaging cadence optimized for planetary surfaces, the mission team found creative ways to synchronize pointing vectors with predicted coordinates of the object. By altering scan angles and exposure times, they captured faint signatures of reflected sunlight from 3i Atlas across several orbital passes. These returns were almost painfully subtle, a cluster of near-invisible pixels shifting just enough between frames to reveal motion. Yet each new capture refined estimates of size, surface roughness, and tumbling behavior. From these high-precision glimpses, scientists extracted a surprising insight. The object's rotational wobble seemed to diminish slightly as it passed near Mars. The effect was tiny, barely above modelling noise, but consistent. Something about the heating it experienced during that segment, perhaps a localized pocket of sublimation, had changed its rotational state. This tiny change added credibility to the theory that internal cavities existed beneath its crust reservoirs of frozen volatiles sealed by millennia of exposure to the interstellar medium. While HiRISE offered microscopic visual detail, MAVEN's ultraviolet sensors provided the heartbeat of 3i Atlas. MAVEN was designed to monitor the Martian atmosphere's slow escape to space, analyzing the effects of solar wind and ultraviolet flux. But these same instruments, sensitive far beyond visible wavelengths, detected faint UV scatter from the object as it passed through a geometry that briefly aligned it with the sun's glare. This was no ordinary reflection. It carried spectral features hinting at exotic chemistry traces of hydrocarbons, broken down into simpler radical signatures of silicate dust, heated by solar radiation, and an emission profile that did not fully match any known solar system comet. What made the UV data especially valuable was Mars's position relative to the Sun. At the time of passage, Mars was located off the ecliptic by a comfortable margin, giving MAVEN a vantage impossible from Earth, while Earth-based telescopes would later struggle against atmospheric distortion and low-phase angle glare. MAVEN observed the object at a geometry that sharpened contrast and amplified its ultraviolet scattering. This allowed scientists to isolate individual molecular signatures, tiny whispers of the object's primordial composition. Even the aging Mars Odyssey orbiter contributed unexpectedly. Its Themis instrument, normally used for infrared surface mapping, captured weak thermal signatures from 3I Atlas during its closest approach. These readings revealed temperature gradients across the object's surface that did not align with rotational illumination alone. Some portions warmed in patterns inconsistent with a coherent shape. This lent weight to the hypothesis that the object's form was irregular, perhaps fractured, perhaps hollowed by ancient sublimation cycles, perhaps even composed of loosely bonded clusters that responded to heat in unpredictable ways. Mars's orbiters became an ensemble cast of complementary instruments, each contributing a layer of detail. And because of Mars's quiet skies, its lack of bright moonlight, and its minimal atmospheric scattering, the data they returned was astonishingly clean compared to Earth-based measurements. But the real transformative moment came when all three spacecraft MRO MAVEN and Odyssey captured data within hours of one another. This overlap allowed for multi-wavelength correlation. Ultraviolet signatures could be matched to thermal variations, which in turn could be aligned with visible spectrum anomalies. For a brief window, Mars became the epicenter of interstellar observation, providing scientists with a dataset richer than any captured for previous interstellar objects. One particular dataset stunned researchers. MAVEN spectrometers detected a narrowband emission spike, faint but consistent, suggesting the presence of an unusually high fraction of supervolatile materials, possibly carbon monoxide or even nitrogen compounds. Such volatiles would long ago have been depleted in most long-drifting interstellar bodies, destroyed by cosmic radiation and sputtering. Yet here they were releasing in delicate pulses. This implied that the object had been shielded by a crust thick enough to preserve ancient ices, yet porous enough to allow selective release when warmed. It was a paradox, a surface too eroded to preserve structure, yet deep enough to protect fragile molecules. And Mars's orbiters were the only instruments close enough or aligned well enough to detect its subtleties. As the days passed, and the object moved farther from the Martian orbital corridor, scientists reconfigured orbital passes to attempt one last coordinated sweep. These attempts yielded dim, grainy data, barely distinguishable from background noise but still valuable. Even the faintest shift in thermal emission or ultraviolet flux helped refine models of the object's mass density and sublimation profiles. While Earth-based observatories would ultimately contribute more data to the broader characterization of 3I Atlas, it was Mars that provided the first clear, unexpected insights, the clues that guided all subsequent analysis. Mars served as an outpost from which humanity glimpsed the deeper architecture of interstellar debris fragments, shaped not only by distant solar systems, but by the silent aeons that follow ejection, when cosmic dust and radiation reshape wanderers into forms alien to any single framework. From its orbit around a barren world, NASA's machines had peered into the passing shadow of a visitor from another star, capturing not just a streak of light, but a layered whisper of chemical histories, structural fractures, and ancient cosmological memory. It was through these Martian eyes that the mystery began to deepen. From the moment Mars's orbiters yielded their multi-layered data, one truth became unmistakable. 3I Atlas was not a simple traveller. Its signals, scattered across wavelengths, stitched together through countless recalibrations, revealed an object governed by hidden geometries and rhythms. The deeper astronomers looked, the more they found themselves confronting a pattern too nuanced to dismiss, and too irregular to classify easily. What emerged was not a single anomaly, but an architecture of anomalies woven into the dust, the reflected light, and the faint emissions streaming from the object's surface. One of the first revelations came from its light curve. Most comets display predictable brightness variations as they rotate, exposing different surface areas to sunlight. 3I Atlas, however, produced a light curve that looked almost agitated, punctuated with sharp dips and sudden flares. These fluctuations did not follow the clean harmonic cycles seen in well-behaved rotators. Instead, they resembled the erratic pulse of a fractured object, whose surfaces were uneven, whose volatile pockets released sublimated material in spasms rather than in smooth jets. But when astronomers plotted these spikes over time, something remarkable emerged. They were not random. Clusters of brightening events occurred at roughly similar longitudinal positions in its rotation cycle. This implied that certain regions of the object, not the whole surface but select patches, were responsible for most of the transient emissions, and these patches appeared to lie on what scientists inferred might be a slanted ridge or a slightly concave depression, a structural feature invisible to telescopes but whispered into existence by the object's changing brightness. Spectroscopy hinted at even deeper complexity. High-resolution spectral decomposition using a blend of Mars's ultraviolet data and Earth's optical observations revealed that the dust, released from 3I Atlas, contained an unusual ratio of silicates to organic residues. Some of the dust grains carried signatures suggesting that they formed under temperatures far colder than anything seen in solar system comets. Others hinted at brief exposure to surprisingly warm conditions suggestive of past heating episodes that defied the slow cooling expected in interstellar drift. In the dust itself, two histories seemed to coexist, one forged in extreme cold, the other marked by brief violent thermal events. Such contradictions demanded explanation. Some researchers proposed that the object had once passed near another star close enough to scorch parts of its surface without fully destroying it. Others suggested that internal processes, perhaps collisions between cavities or crustal collapses, might have momentarily heated certain regions. The dust carried the scars of these events scattered into space in tiny motes, each a message from a distant time. More mysterious still was the pattern of gas emissions. Malvern's ultraviolet detections allowed researchers to deduce release intervals for certain molecular species. Rather than flowing smoothly, the sublimated gases escaped in narrow plumes. Their timing correlated poorly with surface heating, suggesting delayed release from deeper pockets. But the directionality of the plumes presented a puzzle. Many jets emerged roughly parallel to one another, as though oriented along a preferred internal axis. This hinted at a structural memory layers or fractures aligned in a way that preserved the geometry of the parent body, from which 3I Atlas had once been torn. Infrared readings from Mars Odyssey added yet another layer. Themis. Data showed cold zones on the object that remained unusually dark even when exposed to direct sunlight. These regions exhibited heat retention properties far lower than typical cometary crusts. It was as though parts of the object's surface were armoured beneath a brittle insulating layer that trapped heat until it escaped suddenly as gas bursts. This interplay dark zones insulating heat volatile pockets, releasing in fits ridges guiding sublimation, formed a mosaic of complexity unseen in previous interstellar objects. Patterns emerged in the way dust dispersed too. When plotted against the object's trajectory, the dust trail deviated subtly from the expected vector. Instead of radiating out evenly behind the object, it fanned out asymmetrically, forming a faint arc. This arc extended backward but also slightly upward relative to the orbital plane, hinting that dust particles leaving 3I Atlas were influenced not merely by radiation pressure, but by the object's tumbling motion, which imparted rotational velocity to each ejected grain. From Earth, this dust arc looked like a thin veil spreading slowly into emptiness, but the shape revealed critical information. The object's rotation axis was shifting, over time precessing in a way that suggested internal mass redistribution. Something was happening within 3I Atlas, perhaps structural settling, perhaps fracturing, perhaps sublimation, hollowing out pockets that caused the mass to shift. These internal changes, if modelled correctly, allowed astronomers to estimate density gradients and the likelihood of voids within the object. Every simulation confirmed the same unsettling truth. 3I Atlas was far more porous than its spectral signatures would have suggested. The object wasn't solid. It was a survivor of cosmic violence stitched together by weak gravity and the quiet persistence of time. As data accumulated, the mystery deepened further. Some of the gas emission lines hinted at isotopic ratios uncommon in solar system objects. Though preliminary, these ratios suggested the object formed in a region of the galaxy where heavy element enrichment had taken a different evolutionary path. If confirmed, this would mean that 3I Atlas carried chemical fingerprints of a stellar environment that predated or evolved differently from the one that birthed the Sun. It might be older than Earth, older than the solar system, older perhaps than the cluster of nearby stars whose scattered light fills the night sky, in its dust, its gas, its fractured rotation, its asymmetric brightness, and its uneven heat distribution. The object whispered of a long journey through regions of the galaxy, shaped by different stellar histories. Nothing about 3i Atlas was simple. Its structure bore the memory of lost worlds. Its chemistry carried the imprint of ancient stars. Its behavior hinted at internal processes shaped by forces unfamiliar though not supernatural. It was natural but not ordinary, familiar yet entirely foreign. The deeper scientists gazed into its patterns, the more they realized that its anomalies were not merely strange, they were instructive. They offered glimpses of planetary formation on distant suns, of ejected fragments, wandering the void of interstellar chemistry shaped by histories Earth had never known. 3i Atlas was beginning to reveal itself, but with every revelation came a darker question. If this object is only one of countless interstellar wanderers, how many more mysteries cross the solar system unseen? As the data from Mars and Earth accumulated, astronomers finally possessed enough overlapping observations to attempt the most revealing task of all, reconstructing the trajectory of 3i Atlas before it ever encountered the Sun's gravity. To trace its motion backward was to peel away the layers of gravitational influence, stripping off the effects of planets and radiation pressure, until only the raw primordial vector remained the direction the object had travelled through interstellar space for millions of years. But the moment these models converged, the scientific world faced a revelation so unexpected that it fractured assumptions about how interstellar wanderers move through the galaxy. The earlier simulations suggested something disconcerting. 3i Atlas had not drifted lazily into the solar system along a gentle inbound curve. Instead, it approached on a sharply inclined path slicing through the ecliptic at an angle far steeper than 1i Oumuamua or 2i Borisov. Its trajectory seemed aggressively misaligned from the plane where most planetary debris circulates. This was no casual encounter. It was more like a spear thrown from the deep galactic dark, passing near Mars almost by accident. When the modelers traced its motion backward beyond the Sun's influence rewinding time to before, the object felt even the faintest gravitational tug from Earth or Mars. Another unexpected feature emerged. Unlike previous interstellar visitors whose reconstructed paths pointed towards star-forming regions or active neighborhoods, within the galactic disk, the trajectory of 3i Atlas traced back toward a region sparsely populated by young stars. It did not align with any known stellar nursery nor with any recently disrupted system. Instead, its path led outward toward the distant galactic anticenter, an area of the Milky Way where stars are older, colder, and far less active. This alone would have been unusual, but the velocity profile made it extraordinary. Most interstellar objects enter the solar system with speeds clustered around a predictable range comparable to the random stellar motions within the galactic disk. But 3i Atlas arrived faster, significantly faster than expected. Even after removing the Sun's gravitational acceleration and accounting for observational uncertainties, its pre-encounter velocity exceeded the median for local galactic drift. In simple terms, 3i Atlas had been moving through interstellar space with an energy profile no small object should naturally possess. Something had launched it. Something violent, ancient, and immensely energetic. Some planetary dynamicists proposed that the object might have been ejected from a star system undergoing late-stage instability, perhaps when a gas giant migrated inward, scattering debris outward. But the velocity still seemed too high. Others hypothesized that it was expelled during the collapse of a binary system flung outward by a chaotic interaction that tore apart the orbital balance. More speculative theorists suggested a gravitational slingshot around a massive object, a brown dwarf perhaps, or even a stellar remnant like a white dwarf or neutron star. Yet none of these scenarios fully matched the numbers. The backward trajectory reconstruction grew more troubling when researchers added galactic tidal forces to the models. The Milky Way itself exerts subtle directional influences on objects drifting over long timescales. These influences can bend paths, scatter debris, and shift motions gradually across millions of years. When the simulations incorporated the gravitational tides of the galactic disk, the object's path did not smooth into a conventional arc. Instead, it jittered, producing chaotic solutions that diverged the farther back the model ran. This implied that the object had passed through gravitationally noisy regions, areas rich in stellar encounters, or turbulent mass distributions. Some researchers whispered half-joking and half-serious that 3i Atlas looked less like a simple shard from another planetary system, and more like a fragment shaken loose in a galactic event. But even more perplexing details awaited. The object's inbound direction did not align with the typical flow of interstellar bodies relative to the Sun. Most wanderers arrive from the direction of the solar apex, the path the Sun follows through the galaxy. But 3i Atlas entered from a sharply different angle, nearly perpendicular to the expected stream. This is not impossible, but it is improbable. It suggested that the object was not part of the background population drifting through the interstellar medium. It was an outlier, a rogue. Then came the detail that forced scientists to reconsider everything. The reconstructed path avoided all major stellar encounter candidates. When astronomers traced its motion backward for 1 million years, then 2 million, then 5, they found no known star close enough to plausibly have ejected the object at such high speeds. 3i Atlas appeared to have travelled through the void without passing near any major gravitational influence for an astonishing span of time. This led to a startling implication. If 3i Atlas truly originated from a star system, that system may no longer exist. The object might have been expelled from a star that died millions of years ago, perhaps collapsing into a white dwarf or fading into a cooler remnant. Or it might have been ejected when its parent stars drifted apart through galactic migration, dissolving the memory of the system that once held it. In its motion, the object carried geological and dynamical memory of a past erased from the sky. Yet the most haunting detail came from comparing its inbound path with the dust arc detected near Mars. The dust arcing away from the object revealed subtle torques, suggesting that 3i Atlas was still responding to internal mass shifts and sublimation patterns. When these internal dynamics were included in long backward integrations, something remarkable happened. The chaotic jitter reduced. The path straightened, and the object's origin point became sharper. This meant that the internal structure of 3i Atlas, its voids, fractures, and uneven layers had been influencing its spin for millions of years. These tiny torques had accumulated into a measurable deviation over astronomical distances. In a sense, the object had written its own history into its path. Its fractures were not merely geological scars, they were navigational echoes. The reconstructed path pointed not toward a known stellar region, but toward an area believed to once host a small cluster of stars that dispersed long ago. Perhaps the object had been born when those stars were young, flung outward, when gas giants migrated, or when sibling stars drifted apart. Its parent system might have been a scattered memory even before Earth formed oceans, and then, almost as though it had followed an invisible thread, 3i Atlas crossed paths with Mars. To see its trajectory drawn across the sky was to confront a narrative etched in motion, a story of exile beginning in an ancient system that had likely vanished, continuing through millions of years of unbroken darkness, and finally culminating in a chance encounter with NASA's machines orbiting a barren red world. But there was one final twist. When scientists ran forward projection models calculating the object's path after leaving the solar system, they found it would not return to the galactic disk in a predictable way. Instead, its path curved slightly upward toward the galactic halo. Its velocity profile was unusual enough that once freed from the Sun, it would drift into a region of the galaxy sparsely populated by stars, a place where gravitational encounters are rare, and where objects can wander quietly for billions of years without disturbance. In essence, 3i Atlas had entered the solar system as a visitor, and would leave it as a ghost. A fragment expelled from a world long dead, destined to roam regions where no star will warm it again. Its trajectory was not just unusual, it was a record of cosmic loneliness. And in the quiet lines traced across simulation screens, astronomers felt the weight of that immense solitude, a shard of a forgotten system passing briefly through a place where minds could observe it before slipping back into the dark. As 3i Atlas arced deeper into the inner solar system, the questions surrounding its nature did not fade, they multiplied. Every fresh image, every new spectrum, every added data point seemed less like a piece of a puzzle, and more like an added layer obscuring the truth beneath. Instead of clarifying its structure, the object's behavior grew stranger. Instead of converging toward a single explanatory model, the data branched outward into contradictions. It became clear that the mystery was not stabilizing, it was escalating. The deepening turmoil began with the object's intensifying activity. As 3i Atlas neared perihelion, its closest approach to the Sun expectations were straightforward. A typical cometary body would brighten smoothly its tail, lengthening into a shimmering filament as solar heating released newly exposed ices. Yet nothing about this visitor fit the script. Instead of blooming in a predictable crescendo of brightness, 3i Atlas entered a phase of erratic behavior that left both Earth and Mars-based observers unsettled. For several days, the object brightened suddenly far more intensely than predicted, for an interstellar fragment of its estimated size. Telescopes recorded a brief surge, a dramatic flare that made the object momentarily visible to smaller instruments that had previously failed to detect it. Yet just as quickly as it brightened, the flare faded. Within hours, its luminosity shrank to below predicted levels, as though a curtain had fallen over its surface. This oscillation repeated twice, and each time the peaks and troughs came sooner and rose higher. These events baffled thermal modelers. If 3i Atlas were releasing pockets of ancient volatiles, the timing should follow the heating curve determined by its orbit and spin. Yet these spikes came on too quickly and too intensely to be driven solely by sunlight. The pattern resembled not the smooth exhalation of a typical comet, but the agitation of a body under internal stress, like a fractured stone cracking open near a flame. Adding to the escalation, infrared readings showed that the thermal surges were not global. Entire regions of the object remained cold even as others flared with heat, suggesting that some areas were shielded beneath a crust so compact that solar energy barely penetrated. Meanwhile, pockets of the object that did heat appeared to undergo rapid chemical transitions. Organic compounds broke apart in bursts, releasing radicals that contributed to temporary brightening. This selective heating was not merely unusual, it challenged fundamental assumptions about the surface uniformity of small interstellar bodies, but the most disconcerting intensification came from the object's rotation. Before approaching the Sun, 3 Atlas had tumbled irregularly. Its spin state was chaotic but predictable in the way tumbling asteroids often are. Yet as perihelion approached, the tumble quickened. Tiny jets of sublimated gas, previously balanced enough to cause only minor adjustments, now imparted significant torque. This was not surprising. Sublimation often alters spin. What was surprising was the pattern of the change. The object's rotational period shortened abruptly, then lengthened again, then shortened more violently. These shifts were far too large to be caused by the weak jets expected from an exhausted interstellar visitor. Something deep within its structure was rearranging its mass distribution. Cavities might be collapsing volatile pockets, rupturing internal layers, slumping into new positions. The object was in a literal sense reorganizing itself as it moved. The possibility emerged that 3i Atlas was nearing structural instability. Some speculated that the object might break apart during perihelion. Others argued it might shed only surface layers. But the more alarming models suggested that its rotation could destabilize into a catastrophic fragmenting event, one that might release a cloud of debris unlike anything observed in the solar system. Even more unsettling were the object's gravitational anomalies. As its spin accelerated and decelerated unpredictably, its trajectory deviated from projected paths not just subtly but noticeably. Although the deviations remained tiny on human scales, mere fractions of degrees, they were large enough astronomers had to continuously update pointing coordinates for tracking telescopes. This would be manageable if the object's motion followed a coherent physical model, but it didn't. Instead, 3i Atlas veered in ways that implied rapid non-uniform mass loss. Its jets were either far stronger than expected, or were emerging from deeper, more volatile reservoirs than its outer crust suggested. This forced some astronomers to consider an unnerving possibility the outer surface of 3i Atlas had significantly masked the activity of a deeper, more volatile interior. Beneath a radiation-hardened crust, the object might have preserved ancient ices in quantities large enough to produce significant thrust upon release. If true, this object was far closer to a time capsule than a fossil. Its core could contain chemistry frozen since the early days of its parent system chemistry that had never been exposed to starlight until now. As telescopes continued monitoring the object, its gas emission lines grew increasingly unusual. Early spectra suggested ordinary species water vapor carbon monoxide, CO2. But as heating intensified, stranger bands began to appear. Some matched tholin precursor radicals, others resembled compounds seen only in cold interstellar clouds. A few faint emission lines defied immediate classification altogether. Though likely natural, they hinted at chemistry, unlike any observed in solar system comets. This raised a profound question. Had 3i Atlas formed in a region of the galaxy where chemical pathways diverged dramatically from those known near the Sun? Just as its behavior grew more chaotic, so did its dust emission. High-resolution imaging showed bursts of particulate matter erupting from specific regions of the surface, followed by sudden silence. These expulsions produced thin dust arcs that trailed the object arcs that curved and twisted depending on the object's rotation state. One model suggested that dust was being released from radial fissures fault lines that spiraled along the object's surface like stress fractures in an ancient stone. Adding to the escalation, the object began to exhibit signs of nonlinear spin, coupling a phenomenon in which changes in rotation speed feed back into internal mass shifts, creating a cascade of unpredictable torque events. This made 3I Atlas even harder to track as its orientation changed in ways that altered how light reflected off its surface. Finally, as perihelion neared, the object entered a phase best described as volatile agitation. Jets erupted from unexpected regions, dust clouds blossomed and dissipated, rotational states fluctuated violently, and the object's brightness flickered erratically. It was as though the interstellar traveller had been calm only because it was cold, and now awakened by solar heat, it revealed a turbulent interior that had slept unperturbed for millions of years. The escalation was no longer merely scientific, it was existential. Scientists realized they were watching something rare, a body forged in a lost system carrying chemistry shaped by a star long extinguished, undergoing its first real warming in geological epochs. It was not simply passing through the solar system, it was reacting to it, and in its reaction, it revealed that the catalogue of known cosmic behaviours was incomplete, that the universe still held processes beyond humanity's experience. The mystery did not just deepen, it widened, cracked open like the volatile pockets within the object itself, showing that what seemed like a small, silent wanderer was in truth a volatile archive of interstellar history, and it was only beginning to reveal what it carried within. As 3I Atlas neared and passed perihelion, its erratic behaviour ignited a storm of debate across the astronomical community. What had begun as a quiet, improbable detection from Mars' orbit had now matured into one of the most confounding interstellar events since the discovery of Oumuamua. The object's fractured rotation, unpredictable outgassing, peculiar chemistry, and anomalous acceleration demanded explanations, yet every attempt seemed incomplete. It was in this climate of mounting uncertainty that theories began to collide. The first and most cautious interpretation came from comet specialists. They argued that 3I Atlas was in essence an unusually old, unusually battered comet whose volatile pockets had survived interstellar radiation through sheer chance. Such a body, they said, might well behave erratically under solar heating. Its crust could be thick, brittle, and uneven, hiding deep reservoirs of ancient ices sealed there since the earliest days of its formation. Sublimation through such an uneven crust could produce inconsistent jets, wild rotational shifts, and sporadic brightness spikes. This theory, grounded in comets studied within the solar system, explained some but not all of the observed behaviour. Other researchers pushed back. If 3I Atlas truly carried deep volatile pockets, its long passage through interstellar space should have eroded them. Over millions of years, cosmic rays tear apart molecular bonds, sputtering away ices, and breaking down surface layers. To preserve volatiles in any meaningful quantity, the body would need to possess a shielding crust, far thicker or denser than its spectral reflectance suggested. Its appearance was too dark, too porous, too irregular to hide a dense subsurface. And the emission spikes did not align with typical cometary jet patterns. They came too sharply, too rhythmically, and from geometrically consistent regions. This led others to propose that 3I Atlas might not have originated as a comet at all. A competing hypothesis emerged from planetary dynamicists, volatile depletion, and tidal fracturing. According to this view, the object might once have been part of a larger body, perhaps a small moon or icy dwarf planet that had been shattered by extreme tidal forces in its home system. The fragments, irregular and structurally unstable, may have drifted apart and reassembled loosely over millions of years. This process could produce internal voids, weak boundaries, and fractured layers that react violently when heated. The erratic jets observed by Mars and Earth could arise from trapped gases lingering within these ancient fractures. But even this could not explain the object's excessively high inbound velocity. The next wave of theories came from those who studied on gravitational forces in small bodies. These scientists pointed to the subtle, persistent acceleration that appeared to push 3I Atlas outward as it moved through the solar system. This effect, while small, was too consistent to arise from random sublimation. Some suggested that the object's outgassing formed a coherent plume aligned with a quasi-stable internal axis, an echo of how certain active comets eject gas preferentially from specific regions. If 3I Atlas had deep narrow fractures aligned from its formation or fragmentation era, they could channel gas in a directional manner, producing a steady push. Yet even this explanation frayed at the edges. The acceleration profile persisted even during periods of minimal outgassing, suggesting that some force beyond sublimation might be at work. At this point, more exotic theories began to surface not from fringe thinkers, but from respected astrophysicists who had grown comfortable with the strangeness of interstellar phenomena. One proposal drew upon the physics of non-gravitational forces observed in micron-scale dust grains. If the surface of 3I Atlas contained regions with unusual thermal conductivity patches that absorbed and re-radiated solar energy unevenly, the object could experience a variant of the Yarkovsky effect, albeit on a scale not typical for bodies of its size. A massive object like 3I Atlas should not respond strongly to such effects, but if it were unusually porous or hollow with extremely low density, the thermal recoil could be amplified. This hinted at a startling possibility that 3I Atlas might be far lighter than its dimensions implied. A loosely bound aggregate with density closer to aerogel than rock, so fragile that it drifted through space more like a cosmic sponge than a solid asteroid. Others proposed even stranger origins. Could 3I Atlas be debris from a planet that was torn apart by a gravitational encounter with a giant star? Theoretical models suggest that such catastrophic events could produce fragments with unusual density profiles, chunks of mantle or crust stripped free containing exotic mineral compositions preserved beneath layers of fused dust. Such a fragment flung into interstellar space could survive for millions of years if its outer layers were sufficiently hardened. Some went further. They invoked the physics of false vacuum decay, a hypothetical but mathematically consistent event in which regions of space undergo quantum phase transitions. If 3I Atlas had passed through such a region, its chemical structure might bear signatures of altered molecular stability or unusual isotopic ratios. Most dismissed this theory as imaginative overreach, but the fact that it was proposed at all spoke to the object's perplexing nature. Multiverse theorists even speculated whether the object could be a rare survivor of an ancient star formation event flung outward by interactions within dense star clusters. In such environments, young stars pass dangerously near one another. Their gravitational tides can rip apart protoplanetary material, scattering debris with energies impossible in quieter parts of the galaxy. If 3I Atlas came from such a region, perhaps the relic of a system that has since evaporated into the Milky Way's disk, its velocity and composition might indeed reflect an unusually violent origin. But amid this sea of competing hypotheses, one theory stirred particular interest: the idea that 3I Atlas was not a single intact body, but a gravitational aggregate held together by delicately balanced cohesive forces. Such an aggregate would be profoundly vulnerable to solar heating, which could trigger internal collapses, rotational shifts, and unpredictable outgassing patterns. This model explained the erratic flares, the sudden torque changes the asymmetric dust arcs, and the non-uniform thermal response. It also aligned with the observed density anomalies. Yet this raised a deeper question: how had such a fragile body survived the violent ejection from its home system, or the meteor-rich corridors of interstellar space? The answer, some argued, was that it hadn't. It might have been larger once, heavier, stronger. Its current form could be the fossil remnant of a once substantial body, worn down by millions of years of collisions with interstellar grains, cosmic rays, and micro-impacts. Its surface might be the hardened rind of a survivor, an object that had lost mass and structure over time until only its porous core remained. Others insisted that the object's chemistry pointed to something older, still, something forged in the earliest epochs of its home system. Some of its isotopic ratios resembled models of primordial body formation, under conditions very different from the solar system's early environment. If true 3I Atlas was more than a visitor, it was a relic, a geological fossil of a world no longer shining, carrying within it the chemical memory of a star whose light faded before Homo sapiens walked upright. The theoretical battles intensified as perihelion passed and 3I Atlas began to dim. Each model, each hypothesis, each fragment of speculation reflected the same silent truth: this object was telling a story older than Earth, written in dust, ice, and tumbling motion. And though the theories diverge: volatile depletion, tidal fracturing Yarkovsky, drift amplification, primordial chemistry, Each carried the same question at its core. What does it mean that a shard of a forgotten world has wandered into our sky? As 3A Atlas receded from perihelion and its violent flares softened into quieter pulses, a second wave of speculation emerged, less conservative, more daring. These were the hypotheses that crossed the boundary between conventional astrophysics and the vast landscape of the possible. Not wild fantasies, but theories rooted in real, though seldom invoked branches of cosmology and planetary science. In the absence of a single unifying explanation, scientists began exploring the rare, the unusual, and the deeply ancient. And with each new model, the interstellar traveller seemed to reveal another corner of a story that no single discipline could fully contain. One of the earliest exotic hypotheses centered on the idea that 3I Atlas might have been a fragment of a disrupted exoplanet, specifically material torn from the crust or mantle of a small world orbiting close to a massive star. In such extreme environments, tidal forces can shred planets the way black holes tear apart stars. If the object had originated from a super-Earth that spiraled inward during the chaotic dance of planetary migration, its composition might indeed blend rocky minerals with deep, volatile inclusions. The sudden mixing of mantle materials with frozen surface volatiles could explain the contradictory signals crystalline silicates, nestled amid organics, deep volatile pockets, preserved beneath layers that had been violently fused during the fragmentation. This scenario also aligned with the object's unusual density profile. A fragment launched from the breakup of a differentiated planet would not necessarily maintain the neat layering of its parent body. Instead, it would carry an irregular mixture of materials jumbled and pressed together before being hurled into interstellar space. And if that catastrophic event occurred billions of years ago, the resulting fragment would have endured vast spans of cosmic radiation, altering its chemistry into the strange spectral signatures now observed. A second hypothesis pointed toward a different kind of planetary ruin, not the shredding of a rocky world, but the dismantling of an icy moon. In many star systems, large gas giants host populations of frozen satellites, rich in water ammonia and complex organics. If such a moon were torn apart by tidal forces or collisions, its fragments could contain both volatile cores and radiation-hardened crusts. Some planetary scientists argued that the object's behavior, its episodic jets, its fracture-driven rotation changes, its unusually porous interior resembled what one might expect from a segment of such a moon. The combination of rigid outer layers and volatile-rich pockets could produce exactly the inconsistent, sometimes violent sublimation patterns observed by Mars and Earth. This view gained traction when researchers noted that some of the exotic emission lines detected in ultraviolet spectra resembled compounds found in cryovolcanic environments, regions where freezing temperatures shape chemistry in ways not seen in warmer worlds. If 3I Atlas had once been part of a moon with cryovolcanic activity, remnants of that primordial chemistry might survive in sealed pockets only to be awakened when warmed by a new star's light. But other scientists pushed deeper into the realm of cosmochemistry and the early Milky Way. One particularly striking theory proposed that 3I Atlas might be a relic from the galaxy's formative epochs. A survivor from a time before the Sun existed, forged in an ancient system where metallicity was lower, and chemical pathways differed dramatically from those in present-day star systems. The isotopic anomalies hinted at such a possibility. If the object carried ratios of elements formed during the era of second-generation star formation, it might predate many of the nearby stars in the Sun's galactic neighbourhood. In that sense, 3I Atlas would not simply be older than the solar system, it would be older than the cluster of stars that once formed near the Sun. Its journey through the galaxy could have lasted not millions, but hundreds of millions of years. Over that scale of time, an object could drift far from the star that birthed it, especially if that star eventually died, collapsing into a white dwarf, or fading into a quiet ember. The object might then continue wandering through a galaxy, transformed by cosmic evolution, past supernova remnants through shifting spiral arms, across the slow churn of interstellar currents. Others suggested that the object might have originated from a star in the process of dying. When a red giant sheds its outer layers, planetary systems become unstable. Bodies once in stable orbits can be cast outward as the star loses mass. If 3I Atlas had been ejected during such a transformation, its volatile reservoirs may have been flash-heated, then rapidly frozen, producing the strange chemical layers now observed. Under this scenario, the object could represent the last geological remnant of a system whose central star now rests as a white dwarf. A more radical hypothesis emerged from astrophysicists studying high-density star clusters. They proposed that 3I Atlas might have been formed in a region of the galaxy where stellar interactions occur, frequently places where stars fling debris between themselves as they pass. If the object originated in such a cluster, it might have been shaped by gravitational forces far stronger than anything experienced in the Sun's placid neighbourhood. Its velocity, unusually high, even for an interstellar object, could be explained if it had been ejected from a rapidly evolving star cluster where stellar encounters are common and violent. Some theoreticians went further still, invoking fields that rarely intersect with planetary science. They pointed to quantum field models suggesting the existence of cold traps in the deep interstellar space regions, where molecular bonds form under unique conditions not present in planetary systems. If 3I Atlas had drifted through such a region, its chemistry could bear imprints of molecular structures formed in ultra-low temperature environments, preserved beneath its crust until solar heating released them as unexpected emission lines. There was even a brief cautious conversation about false vacuum domains, hypothetical pockets of space where physics might briefly enter lower energy states. If the object had passed through such a domain, the radiation it encountered could alter molecular structures in ways not yet understood. While most scientists dismissed this idea as too speculative, the fact that it was discussed at all spoke to the profound difficulty of reconciling the object's behaviour with familiar models. And yet the most intriguing and perhaps most grounded speculation involved the possibility that 3I Atlas was not a homogeneous object at all. Some researchers believed it might be a rubble pile, a fragile aggregate, held together by microgravity, where pieces from different parent bodies fuse slowly over time. In such a scenario, the object could contain fragments from multiple worlds, each a fossil of a different era in its home system. Its strange mixture of organics, volatiles, and crystalline minerals would then reflect the diversity of the bodies that contributed to its formation, a cosmic archive assembled not by intention but by chance. As the exotic hypotheses proliferated, one theme emerged clearly. 3. Atlas was not merely an interstellar visitor. It was a storyteller. Its motion, its chemistry, and its reactions to sunlight offered glimpses into processes occurring in distant corners of the galaxy, places where worlds rise and fall, where stars evolve and die, where cosmic architecture is shaped not by stability, but by disruption. Its mysteries did not suggest artificiality or conscious design. Instead, they pointed to a natural universe far more complex, diverse, and dynamic than previously imagined. A universe where planetary systems do not simply form and endure, but fragments scatter and leave behind debris that drifts across cosmic time to find new suns and new skies. 3I Atlas was a message not from intelligence but from history, a fragment of a world that no longer exists, carrying within it the physics of environments humanity has never seen, and the chemistry of stars long forgotten. And in that quiet passage through the solar system, it offered a glimpse into a cosmos still rich with unimagined stories. As 3I Atlas retreated from the inner solar system, its violent perihelion agitation cooling into the faint, exhausted glow of a distant wanderer, NASA confronted a narrowing window of opportunity. The object was fading its brightness, dropping faster than expected as it slipped once more into the star-crowded night. Yet its retreat did not diminish scientific urgency. If anything, the need to capture every remaining trace intensified. For the final time, Mars orbit became not merely a passive vantage point, but an active front line of observation. The challenge now was not discovery nor even interpretation, but precision, acquiring data so fine, so stable, that even the faintest residual signatures could be teased apart from the deepening shadows of interstellar departure. This required an evolution in methodology. Instruments designed for Martian climatology and geology had to be pushed to the limits of their capacity, retasked with experimental tracking protocols not envisioned when they were engineered decades earlier. The first step was orbital retargeting. The Mars Reconnaissance Orbiter, after years of meticulously regimented imaging schedules, entered a flexible observation cadence. HiRISE, usually reserved for high-resolution surface imaging, was commanded to shift its gaze more aggressively off nadir tracking 3I Atlas across increasingly elongated exposures. This demanded careful calibration. Too long an exposure would smear the faint object into invisibility. Too short and it would not register at all. engineers developed new motion compensation algorithms' digital corrections for the object's rapid angular drift to stabilize the faint flicker of reflected sunlight against the sweeping starfield. Meanwhile, the spacecraft's context camera CTX provided a broader field counterpart. Though lower in resolution, CTX excelled at capturing diffuse dust envelopes and faint arcs of particulate matter. As 3i Atlas drifted outward, its dust tail, never particularly bright, became even more elusive. CTX's wide-angle captures allowed scientists to map the remaining dust plume at scales impossible for high-rise. The faint arcs it recorded suggested ongoing, albeit diminished outgassing events, final breaths of sublimation escaping from now shadowed interior cavities. But the subtlety of these signatures demanded more than raw imaging. It required new analytical tools. NASA's data teams collaborated with planetary scientists to develop enhanced dust tracking algorithms capable of isolating faint particulate streaks from sensor noise. These streaks, though nearly invisible, carried deep implications. They revealed how dust particles dispersed in response to the object's decaying rotation, offering clues to the internal shifts occurring as temperature dropped. MAVEN 2 entered a new observational mode. Its ultraviolet spectrometers, which had earlier detected the object's unusual emission lines, now struggled to capture even the faintest photons from the receding traveller. But scientists recognized that even minimal UV scatter could yield valuable information. They reconfigured MAVEN's integration times and spectral filters, tuning them to maximize sensitivity to specific molecular signatures, particularly those unexpected lines that had ignited earlier debate. This allowed MAVEN to detect weak emissions inconsistent with typical solar system chemistry, though now too faint for detailed analysis. Still, these faint signatures confirmed that the object continued releasing small amounts of exotic volatiles, likely from pockets gradually sealing shut by cooling crustal layers. For a brief period, MAVEN's instruments captured what some researchers described as spectral afterglow. Not literal luminescence, but lingering traces of high-energy molecular transitions left over from perihelion heating. Mars Odyssey joined the effort with its Themis infrared detector. Though 3i Atlas had cooled significantly, Themis still recorded residual thermal gradients along sections of the retreating object. These gradients, faint but detectable, revealed which regions retained warmth, longest evidence of uneven internal structure. Some areas, likely those insulated by compact crustal layers, cooled slowly. Others, more porous, lost heat rapidly. These signatures offered a final glimpse into the object's internal heterogeneity before it faded beyond Mars's ability to see. As the orbiters gathered their final observations, NASA's computational teams worked to refine tracking algorithms. 3i Atlas was now too dim for passive detection. Instead, trajectory predictions had to be fed into spacecraft pointing systems, with extraordinary precision factoring in projected non-gravitational forces that continued nudging the object off purely Newtonian paths. The orbital elements were updated daily. Residual anomalies in acceleration far smaller than those observed near perihelion persisted enough that constant correction was needed. This revealed something profound even as the object faded, its internal mass redistribution continued. The jets had died, the flares gone, the violent torque events quieted, but the tiny deviations in trajectory suggested that 3i Atlas was still adjusting, still settling into a new equilibrium after the destabilizing heat of solar proximity. What had awakened at perihelion had not fully gone dormant. Dust analysis improvements marked the next phase of scientific refinement. Using data from both Mars and Earth researchers, modelled particle trajectories to reconstruct the object's dust ejection history. These models showed that some dust arcs, those observed faintly by CTX, were composed of extraordinarily fine grains smaller than typical cometary dust. Their distribution suggested that internal collapses, not surface sublimation, were responsible for their release. This strengthened the theory that the object was a loosely aggregated structure, its interior rearranging as temperature gradients shifted. Toward the end of the observation window, the orbiters attempted one final coordinated sweep. This effort, nicknamed the fading capture, involved high-rise MAVEN and Themis, focusing simultaneously on the object's predicted coordinates. The result was a faint but remarkable composite data set. Ultraviolet scatter thermal decay and visible band reflection measured at nearly the same moment. The composite image, when processed, did not resemble a comet or asteroid. It resembled a ghost, an outline of fractured illumination against the dark. In this final phase, NASA's role was no longer to understand the object fully that would require decades of analysis, but to ensure that nothing was lost. The orbiters became archivists. The algorithms became custodians. Every photon recorded became a fragment of a cosmic biography, a relic of a world that might have vanished long before Earth formed oceans. The tools sharpened in Martian orbit did more than capture a fading visitor. They expanded humanity's observational ability beyond Earth, proving that interstellar studies need not be confined to the home planet. Mars' silent ancient patient had once again become a witness, and through the instruments it hosted, it had captured details impossible from any other vantage. When 3i Atlas finally dimmed below detectability, the orbiters turned back toward their Martian duties. But they had changed. The software updates remained, the tracking algorithms persisted, the new calibration libraries stayed aboard. Mars had taught NASA something unexpected, that a planet without life could still serve as a partner in cosmic observation. And in the wake of 3i Atlas, the stage was set for the next wanderer and the next mystery to be caught by Martian eyes. By the time 3i Atlas slipped past the orbit of Mars for the final time, its once vigorous flares had quieted into a faint dwindling glimmer. The object no longer dazzled or startled. Instead, it receded with the weary calm of something ancient returning to its long exile. Yet in its fading wake, it left behind an echo, a data-rich afterimage that would amplify scientific debate for years. The object itself was disappearing, but its residual signatures had only begun speaking. On Earth and Mars alike, astronomers turned from real-time tracking to deep analysis. Across laboratories, observatories, and mission centers, data previously overshadowed by the object's dramatic perihelion behavior came back into focus. Scientists re-examined dust arcs, recalculated rotational shifts, refined heat loss curves, and reprocessed spectral fragments that once seemed too faint to matter. Every scrap was now a clue, every anomaly a doorway. 3i Atlas had outrun the solar system's light, but its echo remained. The first step toward understanding this echo came from revisiting the dust arcs captured by Mars's CTX camera. At first, they had seemed like irregular streaks, artifacts of outgassing bursts or chaotic rotation. But when researchers layered CTX data with Earth-based imaging taken weeks apart, a coherent structure emerged. The dust arcs, faint and asymmetric, aligned along a plane tilted relative to the object's trajectory. This plane appeared to correspond to a fracture network and internal geometry that had governed not only how dust escaped, but also how the object redistributed mass as it warmed. In effect, the dust preserved a map of the object's internal architecture. Further analysis showed that the dust arcs diverged subtly as they drifted outward, not due to standard radiation pressure, but because grains of different composition reacted differently to solar heating. Some grains, likely silicate-rich, maintained their trajectories longer. Others, rich in organic residues or fragile volatiles, curved sharply, as though responding to sublimation long after their release. This diversity hinted at compositional layering within 3i Atlas, more complex than any simple rubble pile model predicted. Meanwhile, Themis thermal data revealed cooling curves unlike those of typical asteroids or comets. Instead of a smooth radiative decay, 3i Atlas cooled in pulses. Thermal hotspots dimmed abruptly, then plateaued, then faded again. These pulses corresponded to areas where internal voids had likely collapsed as the object cooled, shifting mass inward and altering heat flow. Such thermal stair-steps are seldom seen in small bodies. Their presence here suggested that 3i Atlas may have contained cavities large enough to collapse under changing thermal stress. The object had not simply cooled, it had settled. These settling events were mirrored in photometric studies from Earth. Light curve reanalysis showed tiny persistent oscillations in brightness that continued long after perihelion. These oscillations were too regular to be random, too faint to be active jets, yet too persistent to ignore. Some hypothesized that these flickers were the surface signatures of microfractures closing as the object contracted. Others suggested that debris newly shed from the surface occasionally drifted through the line of sight. Either explanation reinforced the same emerging conclusion: 3i Atlas was evolving even as it receded. Spectroscopic echoes provided the next revelations. As the object faded, Earth's large telescopes captured only fragments of its spectral profile. But when researchers stacked dozens of low-quality spectra into composite form, obscure features, emerged features hidden beneath noise when viewed in isolation. These composite spectra revealed faint absorption lines consistent with carbon chains damaged by cosmic rays. Their degradation profiles resembled structures found in interstellar molecular clouds, yet modified by heating cycles that suggested the object's volatiles had been sealed and resealed over millennia. This dual-signature cosmic ray damage layered atop thermal processing was rare if not unprecedented. It implied that 3I Atlas had spent long epochs in both environments, deep cold clouds where chemistry freezes into delicate chains, and sudden heating events where those chains break apart. Perhaps the object had drifted through a dense molecular cloud at some point in its past, accumulating exotic compounds before being expelled again into emptier regions. Or perhaps its parent system had once orbited near such a cloud before being disrupted. Whatever the case, the dust and gas released near perihelion carried traces of a chemical journey far longer and more varied than could occur in the solar system alone. The final layer of residual analysis came from the object's long-term projected trajectory. With fresh data from its fading phase, dynamicists recalculated its outbound path with higher precision. Once free of the Sun's influence, 3I Atlas would not return to the galactic disk in any predictable fashion. Instead, its path arced up toward the halo, toward a region sparse in stars, cold in radiation, and rich in gravitational quiet. The object had arrived from a turbulent region of the galaxy, but would leave towards silence. The outbound vector implied something profound. 3I Atlas would not encounter another star for tens of millions of years, if ever. It was now on a path that would lead it into the interstellar desert's vast regions, where dynamical interactions are rare, and where objects wander unperturbed for cosmic time. Whatever internal shifts had occurred at perihelion would be the last major changes it would experience for epochs uncountable. Its fading was the beginning of another long sleep. Astronomers realized they were watching not only the end of an observation window, but the closing of a geological chapter. The data harvested in its final visible weeks would be the last humanity ever gathered from this fragment. No probe would chase it. No telescope would see it again. The echo captured by Mars and Earth would be the only record of its brief illumination. What remained was a tapestry of clues, dust arcs tracing fracture networks, thermal curves revealing voided interiors, spectral layers hinting at ancient cosmic migrations, and a final trajectory pointing toward a future of quiet wandering. These echoes did not solve the mystery of 3I Atlas, but they did something more valuable. They preserved its story. Though incomplete, though filled with contradictions, though rich with unanswerable questions, the object's fading signature formed a coherent truth. 3I Atlas was not simply a visitor, it was a remnant of worlds lost of systems dispersed of epochs forgotten, and in its brief encounter with the solar system, it had left behind a map of its own survival, a map written in dust fractures and spectral ghosts, a reminder that the galaxy is full of stories older than stars. As 3I Atlas faded into the dark beyond Mars's orbit, its diminishing glimmer marked not an ending, but an inflection point, an invitation for reflection across the scientific world. What had begun as a whisper in Martian telemetry had become a confrontation with the vastness of cosmic history. The object's retreat into interstellar night left astronomers with an unsettling awareness that the solar system, quiet and insulated though it may seem, is merely a temporary harbour in a galaxy thick with ancient wanderers. And as the last photons reflected from its surface reached Earth's telescopes, the deeper meaning of its passage began to crystallize. 3I Atlas had not come bearing revelations. It brought no grand answers. It did not rewrite physical law or unveil hidden orders of the cosmos. Instead, it did something more subtle, something more powerful. It forced humanity to consider the sheer diversity of planetary histories beyond the Sun's realm. In its fractured dust arcs, its volatile pockets, its strange isotopic signatures, and its unpredictable rotation, 3I Atlas carried the memory of places that no longer exist. It was a fossil drifting between stars not fossilized in stone but in motion chemistry and silence. The scientific significance lay not in what it was, but in what it represented. For centuries, humanity believed that planets formed quietly, lived quietly, and died quietly, each system an isolated island in a vast void. But the passage of interstellar bodies first, Oumuamua, then Borisov, now Atlas, revealed another truth. Planetary systems are not static. They shed pieces of themselves through gravitational violence, stellar evolution, and chaotic interactions. These fragments, stripped away by forces indifferent to the lives of the worlds they destroy, become seeds of cosmic memory. They drift outward, cross the gulf, and become part of a larger galactic ecology, one shaped not by life, but by loss. From this perspective, 3i Atlas was not a visitor, it was an emissary of entropy. Its existence testified to the fragility of worlds. Somewhere long before Earth cooled into oceans, a star restructured itself through gravitational collapse, or a gas giant migrated inward and tore apart smaller bodies, or a cluster of youthful stars exchanged debris in their crowded infancy. In that event, whatever it was, 3i Atlas was cast outward. For millions of years it wandered, carrying the geological signature of its origin, like a note folded into its core. Not a message for anyone, not a deliberate archive, but a remnant of cosmic change. Its brief warming near the sun did not reveal its story, it reactivated it. The jets that erupted near perihelion were not events of the present, but echoes of the past, releasing compounds shaped by ancient processes into the solar system's airless vacuum. The fracture patterns traced by dust arcs were the geometry of its forgotten birth. The isotopic ratios hinted at stellar metallicities that belonged to another era of galactic evolution. Even its final trajectory, pointing toward the halo, toward silence, spoke of an exile far older than human imagination comfortably grasps. Seen this way, the mystery of 3i Atlas was not that it was strange. The mystery was that it existed at all. And as scientists sifted through its fading signatures, humanity found itself confronting an older, more philosophical question. What does it mean to witness something that predates not only human civilization, but Earth's very continents? When a fragment of another world slips into our sky, what does it reveal not only about the universe, but about our place within it? The answer, though quiet, is profound. It reveals that the Milky Way is not a static backdrop, but a living archive. Its stars are storytellers, its debris fields are libraries, its interstellar wanderers are chapters that move freely, sometimes landing by chance alone, in the eyes of a species able to read them. The encounter with 3i Atlas underscores humanity's fragility and significance simultaneously. Fragility because Earth is no more protected from cosmic upheaval than the world that birthed Atlas. Significance because despite the enormity of the galaxy, consciousness arose here, consciousness capable of recognizing that a fading speck of light carries the memory of long-dead stars. What questions remain unanswered? Almost all of them. We do not know its parent world. We do not know its age. We do not know what events shattered its original form. We do not know whether its chemistry points to environments rare or common across the Milky Way. And we certainly do not know how many more such fragments pass silently through the solar system unobserved. But in the quiet after its passing, a subtler truth emerges. Every interstellar visitor is a reminder that our solar system is not alone in its story. It is one thread in a tapestry woven across the galaxy, one star among hundreds of billions, one cradle among millions of worlds, one chapter among countless others. And 3i Atlas, a shard of some lost system, became the brief intersection of two cosmic narratives, one ancient, one young. Its fading spark tied them together. As the last traces of 3i Atlas slipped beyond the reach of Mars's orbiters, the solar system settled once more into its familiar rhythms. Quiet arcs of planets, cold stones circling in the Kuiper belt, long shadows cast across empty space. The object itself, now little more than a dim memory etched into data archives, drifted outward into the dark. Its path lengthened into a gentle curve, carrying it toward a region where even starlight thins, and where its fractured structure will cool into stillness again. The excitement that once flared around its passage slowly softened into contemplation. Scientists turned off enhanced tracking algorithms. Telescopes pivoted back to nearer targets. The fever of discovery faded into the steady hum of analysis. And in that slow settling, something calming took root, a reminder that the universe does not rush. Its stories unfold across spans so vast that even events of extraordinary significance must eventually exhale into quiet. In the softening of that moment, 3i Atlas became less a mystery to solve and more a presence to remember, a faint visitor, a drifting archive, a reminder that the darkness between stars is not empty, but filled with remnants of worlds long vanished. Its passing encouraged a gentler perspective, the understanding that humanity in all its urgency exists within a cosmos that moves with patient inevitability. There is no need to grasp too tightly, no need to force certainty where the universe prefers openness. And so the object fades, not in sorrow but in serenity. Another traveller returns to the silence from which it came. Another chapter closes, allowing the next to emerge when the galaxy permits. For now the sky grows still again. Sweet dreams,